So in this video, we're going to look at exponential solutions. In other words, these are the solutions to our capacitor discharge over a fixed resistor. So we were seeing in our last video that we kind of came up with these equations for how our charge on our capacitor kind of decreases over time. And we said these equations were pretty good, but they kind of were some limits on how they worked. So we kind of needed that this quantity here was kind of small, really. We need a small enough time interval so that our proportional drop in charge isn't too big. In other words, that the charge on our capacitor hasn't changed too much from what it was. If that decrease is kind of small, then these equations kind of work. But otherwise, if we think about too long a time interval, or the charge decreases very quickly, let's say we've got a very big charge over it, initially, then this isn't going to work too well. And there's a way of being a bit more precise about this and getting a bit more accurate. Now, we don't need to worry about it too much, but we'll just briefly skim over what happens. So we were saying really that this will kind of worked all right as long as our time interval wasn't too big. There's a little bit more to it than that, but we don't need to worry about it. So all we do is we just consider making our time intervals smaller and smaller. So what we do is we consider very short time intervals. So in other words, we let this delta t basically go towards 0. And what this is going to do is going to transfer this equation that we saw, this, sort of the change in our charge divided by the time taken, which we were calling a bit like a rate of change, but is not quite there if our delta t is quite big. This is kind of like the average change, the average rate of change of our charge over a time period. If what we do is actually we let this delta t go to 0, then we get a differential equation. And now this is something, if you're not doing A-level maths, you probably won't know what this is and you don't need to worry about it. But what this is this just means this d, this little d, is like a bit like that delta symbol we've got there, but this means kind of at a moment in time. So this delta q over delta t kind of means consider, say, the change over a second, how much charge decreased by that point, how much did your charge change, divided by the time interval you're talking about. This means at a point in time, so t is 2 seconds or 3 seconds, at any point, how is your charge changing? This is a bit like the gradient of a graph at any point. So this dq over dt, that is just like, if we go back to our exponential solutions, that is effectively the gradient of any point on this graph at a point. So if we worked out what the gradient of this line was here, dq over dt would be that gradient at that point. Now, that's all we're going to say about it. We don't need to do much, but it's a differential equation, and because of that, we can solve it. If you've done A-level maths, you'll kind of see this stuff. If not, don't worry about it. So there's a solution to this equation, and this is a good solution. So, and the point is this will work always. We were saying, previously, these kind of equations kind of worked if we were considering a small enough time interval, or rather that our change in charge wasn't too big. We're going to come up with an equation that's always true, and it's going to give us the charge on our capacitor at any point in time. And this is the solution we find. If we solve this equation, we find that Q, which is the charge on our capacitor at any point, is equal to the original charge on our capacitor times by this thing here, this exponential function. That's e to the power of minus t over rc. So that's the solution to this equation.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.